All right, let's dive right in. We're about to journey to the heart of a cosmic lighthouse, a spinning star so dense, so incredibly fast, it almost defies imagination. It's called a pulsar, and deep inside it, there's a secret, a mystery, that has stumped scientists for decades. Today, we're going to try and crack that case.
I mean, just try to wrap your head around this. You've got an object with more mass than our entire sun, but it's been crushed down into a space the size of a city, and it's spinning faster than a kitchen blender on its highest setting. The forces at play here are just astronomical. It is literally one of the most powerful engines in the entire cosmos.
But for all that incredible power, there's a really simple, fundamental question we still don't have a solid answer to. We see these powerful beams of radiation that pulsars shoot across the universe, right? But where, exactly, do those beams actually start? That is the mystery we are tackling today.
People in the field call it the lighthouse mystery. Think about it. We can see the beam of light sweeping past us from thousands of light years away, but we can't tell where on the lighthouse the bulb is actually located. Is it at the bottom, the top, somewhere in between? Figuring this out is a huge challenge in astrophysics.
So just as a quick refresher, a pulsar is what's left after a massive star dies. It's a spinning neutron star, and its magnetic poles act like these cosmic spotlights, shooting out intense beams of radiation. As the star spins, those beams sweep around the cosmos, and if one of those beams happens to flash across our line of sight here on Earth, our telescopes see a regular, repeating pulse of energy. It's a perfect cosmic lighthouse.
Now, every good mystery needs a clue. And in this case, scientists found a really clever one hidden right there in the light itself. It's a tiny, almost impossible to see timing shift, and it's all caused by the pulsar's extreme physics. The effect has a bit of a mouthful of a name. It's called aberration retardation.
And pretty much everything hinges on this one effect. By measuring this tiny little shift in when different parts of the signal get to our telescopes, we might actually be able to map the physical structure of where the beam begins. You could say this AR effect is our smoking gun.
Okay, so let's break it down. The first part of the clue is aberration. Because the source of this radiation is spinning so unbelievably fast, the beam itself gets kind of bent forward, in the direction of the rotation. It's a lot like how rain seems to fall at an angle when you're running through it. Same basic principle, just on a cosmic scale. The second part of the clue is called retardation, and this one is really just about distance. The idea is that different parts of the signal might be emitted from different altitudes above the star's surface. So if that's true, the light coming from higher up has a little bit farther to travel to get to us, and that creates a minuscule delay in its arrival time compared to the light from lower down.
So here's how it all comes together. The theory goes that a pulsar's beam isn't just one uniform thing. It has a central core and then these outer cones, and they're likely emitted at different heights. So when you combine the bending from aberration and the delay from retardation, you should get a predictable, measurable timing shift between when we see the core and when we see the cones. If we can measure that shift, we can actually calculate the height difference. Pretty cool, right?
Okay, so with this AR theory as their roadmap, a team of astronomers launched what was basically a galactic investigation. They set out to hunt for this tiny timing effect in pulsars all across our galaxy to see if the theory actually holds water.
And this was no small task. They put together a lineup of 23 suspects, a really diverse group of pulsars. They used data from some of the world's most powerful radio telescopes, like the GMRT and the legendary Arecibo Observatory. And their mission was simple: perform incredibly precise measurements on each one and look for that telltale timing shift.
So after all that work, what was the verdict? Well, the results came in, and they provided some really powerful evidence for the theory. But, just like in any good mystery, the clues didn't all point in the exact same direction. There were a few outliers.
The evidence was pretty compelling. For 7 of the 23 pulsars, the AR effect was there, clear as day. For another 12, there was a really strong tendency in that direction. So you're talking about 19 out of 23 pulsars basically supporting the theory. But that left 4 pulsars that were just clear counterexamples.
The researchers themselves concluded, and I'm quoting here, "It appears that the AR effects are likely to operate in most pulsars from our sample." And that was a huge step forward. But in science, you have to account for all the data. So what was going on with those 4 outliers?
And this is where the real detective work had to begin. Those 4 outliers couldn't just be ignored. They hinted that the story was a bit more complex. One pulsar in particular, a really stubborn case about 5,000 light-years away from us, turned out to be a real head-scratcher.
So let's zoom in on one of these outliers, Pulsar B1859+03, which you can find in the constellation Aquila. This particular pulsar became a critical piece of the puzzle because it just refused to fit the model. And the reason why really shows you how tricky this kind of science can be.
So here's the problem with B1859+03. It has what astronomers call a partial cone. What that means is the entire trailing half of its signal profile is just gone. It's missing. Now, to measure that A shift, you have to find the center point between the leading part of the signal and the trailing part. But with no trailing signal, well, the calculation is literally impossible. This pulsar was holding on tight to its secrets.
But even with these really difficult cases like B1859+03, the overall trend was still clear. And finding that AIR effect in the vast majority of pulsars has some pretty profound implications for what's happening at the very heart of these incredible stars.
Okay, this is the key takeaway. If the AR effect is as common as it seems to be, it basically confirms the model. The central core of the beam is created closer to the star's surface, while the outer cones originate from a higher altitude. For the very first time, we're actually starting to map the 3D structure of this amazing engine.
But of course, good scientists always check their work. And it turns out there's actually another way to estimate the emission height. Besides our AR timing method, there's also a geometrical method, which uses the width of the pulsar's beam to calculate the very same value. So you've got two different tools to measure the same thing.
And here is the final twist in our story. When the researchers compared the results from the two methods, they didn't match, not even close. The geometrical method consistently calculated a much higher emission altitude than the HR timing method did. The two sets of clues were pointing to completely different answers.
So, why the disagreement? Well, the paper suggests a pretty fascinating possibility. What if one of our basic assumptions is just wrong? The AR method kind of assumes that the core signal starts right at the star's surface. But the researchers crunched the numbers and realized that if the core emission actually begins about 100 kilometers above the surface, the two methods suddenly snap into perfect agreement.
And that right there is the beauty of science. Solving one mystery just opens the door to an even deeper one. The researchers concluded their paper by calling for more studies to resolve this exact question. The case is definitely not closed. So this is where we're left. We started with what seemed like a simple question. Where does a signal begin? And the search for an answer took us thousands of light years away, where a timing shift measured in microseconds is allowing us to map the engine of a dead star. It just goes to show you, sometimes the biggest secrets the cosmos is holding are hidden in the absolute smallest of details.